Hey, Physics 30s, how's it going? So I'm just going to start this going over the practice questions for particle EMR here. Started to use this new program to record. The other one kind of went a bit flaky on me. So hopefully we can work through this. I just don't like the idea that this camera is not flipped. It makes it a little bit hard for me to gesture properly. Anyway, what is the energy of a photon with a wavelength of 450 nanometers? I'm going to pull up my formula sheet here. I'm going to look at the top right corner here, right up in this corner up here. Okay. There's a bunch of formulas that we're going to be using. There's some formulas down here in the bottom as well that we're going to be using as well down here. Oops, there's the problem with this. So this one up here and this one over here. So what we have, we want to find the energy of the photon. So the energy of a photon could be calculated by going, let me just get my pen the right way. We can go E is equal to HF. Now, depending on which H you use, depends on what unit of energy you get out. So if I use, say, electron volt version, which I'd like to use because that's a very good communication tool, so the 4.14 number, electron volts per second here. Again, that number can be found on the constant side. Oh, excuse me, right here. All right. So it's two versions here. You got the joules per second, and the one below it is the EV per second one, or EV second. So we're going to use that one in this situation. And rather than using the HF, because I have the wavelength, I'm going to have to use the HC over lambda formula. So I'm going to put in here times 10 to the 8, and I'm going to divide by 450 nanometers in meters because the meters per second as well. Okay, so I punch that all in, and I should get a nice number of electron volts here. Yeah, so I get 2.76 electron volts. Now, most of the time, we're going to be using electron volts to communicate our answers, to put it in boxes. The joule version of this number we use only really for the mathematical process. Like we might use it to calculate, okay, how fast is the electron going if it gained this much energy? Or what is the momentum of this electron or this photon? It's really only two times you ever use it that way, or the joules. What's the wavelength of a photon with this very specific amount of energy? So I just rearrange that formula there. HC over E. Okay. Let's put our numbers in there. So we have the EV version here. So I'm going to have to change, put it 4.14 here again. EV seconds. We got the speed of light again. And we are in electron volts here. So I'm okay with that. Sometimes they give you like mega electron volts or kilo electron volts. You're going to see those later on, or even giga electron volts. Things with immense amount of energy. Well, in terms of subatomic particles. So what we have is 8.28 times 10 to the negative 8 meters. If I change that to nanometers, it's like 82 nanometers. 82.8 nanometers. A lot of energy, so that's why it's such a short. Well, compared to the one before, it's a lot of energy, so it's a shorter wavelength. Compare the energy of a photon, that's 300 nanometers, to an energy that's 600 nanometers, and which photon is more energetic, and by what factor? So it's like 2 times or 3 times, or is it half as much? So it looks like it's shorter wavelength, so it's got to have more energy. So I'm just going to quickly calculate those two energies. So for the 300 nanometer one, and for the 600 nanometer one. Oops, yeah. HC over lambda. So I'm not going to bother showing this substitution here, so I'm just going to type the numbers in. 300 nanometers, yeah. So 4.14 for this first one. electron volts. And let's just change that one number in there. 2.07. You can always see that, yeah, the one that has half the wavelength has twice the energy. So the 300 nanometer, oops, is twice as energetic. I'm going to put down a little since here, since it has half the wavelength. Oh, a little G in there. Okay. Let me fix that up there. Yeah, I'm not liking the fact that I'm looking that way. There we go. How about that? Is that better? A little better. Okay. What is the frequency of a photon that has a energy of 100 kilovolts? So here's something a little bit larger than usual. What part of the spectrum do you think that's actually from? Okay, so what we want to do the frequency one. So E is equal to HF. F is equal to E divided by H. And we're in kilo electron volts again, so we're going to use our, first I'm going to times it 10 to the power 3. And then I'm also going to be using the 4.14 number. Cool. So 100,000 divided by 4.14 e to the negative 15. Okay, so we get our frequency of 2.42 times 10 to the 9. Ooh, that's a horrible 10 there. 10 to the 19 hertz. But what I'm going to do here is I'm going to change this into wavelength, because I'm not too fond of determining what type of spectrum it is from the frequency. So I'm going to be using C is equal to F lambda to find out what my lambda is. So I'm going to go with the speed of light divided by my number here. So I get 1.242 times 10 to the negative 11 meters. If I change that just into nanometers, so I'm going to divide by 10 to the negative 9, I get 0.01242 nanometers. Okay. And then I'm just going to, well, it's obviously on the shorter end of the visible spectrum, so it's into the ultraviolet / X-ray range. I'm just going to look up the EMR spectrum here. Right. What you're going to really have to expect to memorize is what are the ends of the visible light. The other stuff is kind of wishy-washy, so depending on which spectrum you look at, you might find different numbers for this stuff. Let's see if I can find a good one here. So what do we have? 10 to the negative 11. Yeah, it kind of looks like we're on the edge of X-rays and into the gamma rays. Oh, actually, those are the centimeters. I wonder why they did it that way. Let's find a different one here. Are these are meters? Yeah, these are the meters. Yeah, we're right in the X-ray range here. So this is an X-ray. Like, according to this one I'm looking at here, 10 to the negative 12 is at the end of an X-ray. So it looks like we're going to be at an X-ray. There we go. X-ray. Awesome. Okay, how many photons are emitted by a 100 watt light bulb in 10 seconds? So first of all, what I'm going to do here is change this power into energy by taking the 100 watts. That's 100 watts there. Times it by the 10 seconds. Oh, geez. Let me just fix all of my units here. Times it by my 10 seconds. So I get 1,000 joules of energy there. Okay. Now, what I'm also going to do is determine how much energy this photon is. So Hc over lambda. Because it's in joules, because the energy down there is in joules, I'm going to have to use the 6.63 number this time. So I'm actually going to write that in there. 6.63 times 10 to the negative 34 joule seconds times the speed of light divided by the wavelength. 550 times 10 to the negative 9 meters. Okay. Cool. Okay, so the energy of this photon is 3.616 times 10 to the negative 19 joules. I have to figure out how many of these smaller numbers can fit into this large number here, this 1,000. So I'm going to take these two numbers, so let's just say n photons, this would be the number of photons, is equal to 1,000 joules divided by this 3.616 number. You're always going to get a whole number, like a gigantic number of photons out of this kind of calculation. So in this case, I get 2.36 there, so 2.6 or 2.77, sorry, times 10 to the 21 photons. Yeah, it's quite a big number there. Okay. So hopefully that was, hopefully you did well in that worksheet. I'll see you in the next one. Bye.